Hello, my name is Junpei Nishikawa from Shizuoka University, Japan. This is a pre-recorded presentation for the 2022 International Conference on Cognitive Modeling. I'm going to talk about estimating phonological awareness with interactive cognitive models, feasibility study manipulating participants' auditory characteristics. This study is a part of the studies aiming to develop a method of constructing a cognitive model adapted to the individual phonological problem. I'd like to begin with background about our study. Recently, it has been pointed out that a diverse society is important. Society is made up of individuals with a diverse innate base, and their experiences differ from one another. To communicate smoothly among diverse individuals, they need symbols shared by society. A typical example of the use of common symbols is language. During language development, immature children make errors in speech. And the patterns of these errors are varied from child to child. For example, Blandin reports cases of consonant deletion. She says that cat, hat, and pat sound the same, which means that the speaker doesn't recognize silent consonants, but only vowels. There is also cases of sound confusion. It has been reported that Japanese children are confused between ra and da. This process of language development, or the error in the process, can be explained by the keyword phonological awareness. I also show here the Japanese example. In Japanese, the common unit is the mora. The word ringo, ringo means apple. Ringo is consisted of 3 sounds, 3 morae. Like this. Japanese is convenient for this kind of problem because it has a clear connection between sounds and letters. This study focuses on the Japanese language. As shown in this example, phonological awareness is the ability to recognize and treat a sequence of sounds as a series of units. It can be defined as the degree of sensitivity to sound structure of oral language. The formation of phonological awareness can also be delayed by disorders such as autism and dyslexia. Many studies of phonological awareness have been conducted. These studies measured phonological awareness using not only phonological manipulation tasks and short reading tasks, but also popular word game. These are reports from clinical practice and experimental psychological approaches, and the internal processes and mechanisms are still not well known. Understanding the mechanism may be necessary to support language development. To understand the mechanism, we believe that cognitive modeling is effective. We follow a cognitive modeling approach to understand the mechanisms of phonological awareness. We use traditional cognitive architecture to build phonological awareness models. This is because cognitive architecture allows us to build a variety of models on a common ground. To cope with the various difficulties of reality, we need a personalized and diversified model. This can be addressed by using cognitive architecture. We use Actal in this study. Actal has symbolic and sub-symbolic components, and we think that the sub-symbolic components can be used in personalized models. So here are the aims of this study. Ultimately, this study is a part of the studies aiming to develop a method of constructing a cognitive model adapted to the individual phonological problem. To this aim, this presentation proposes a method of selecting a cognitive model and fitting it to individual phonological problem. The method is validated through an experiment in which participants' auditory traits are artificially manipulated. Finally, we discuss the feasibility of using the proposed method. I'll talk about the task and the model. The model performs a word game called Shiritori. This is a popular word game in Japan. The player recognizes the last sound of a word and answered with another word starting with that sound. For example, the last sound of lingo is go. So the next word must start with go, such as gorilla. Using Shiritori and Actual, we constructed this model. The model uses the general memory retrieval mechanism implemented in Actual to represent immature phonological awareness that fails to Shiritori. The model has knowledge of this network structure. To play Shiritori, the model searches for a word by tracing this network from the word it has via the knowledge of the sound. For example, from lingo to gorilla via go. To represent immature phonological awareness, the sound knowledge has a similarity. We assume the model answers O ni for lingo because it incorrectly searches for similar sounds. We consider two factors for setting the similarity: distinctive features and similarity impact. These two factors personalize the model. Distinctive features are representation of sound discussed in phonology, and in this model, we use them to characterize a sound as a vector. We defined two ways to represent a sound: concatenation and average. We also consider the coefficient of impact of similarity on this sound representation. Based on the above models, we propose a support system for the formation of phonological awareness. An overview of this system looks like this. The system contains several models with individual error patterns. Here is how it works. The task is Shiritori. The user responds to a spoken question by selecting the appropriate choice. The user also clicks on the choice and clicks on the choice and makes a decision based on the audio. These choices are made from the answers returned by the models in the background. Using this system, we estimate the user's phonological awareness through Shiritori task. The system selects a model with a structure similar to the user's based on the number of times the user selects answers. During the estimation, the model is updated to be closer to the user. After a certain number of Shiritori tasks, remove unselected models and add new ones. The added model will inherit the setting of the well-selected models with some adjustment. For example, remove model 4 and model 5 inherits the similarity table of model 1, and the similarity impact is set a little lower. This process is repeated to select a model with a structure that corresponds to the user. After estimation, the system uses a model to support the formation of phonological awareness. Here, we assume that the user will continue with the Shiritori task by adjusting the difficulty level. By referring to the model that correspond to the user's phonological awareness, the system can present less confusion choices or adjust the percentage of questions that can be answered. We conducted feasibility experiments on the developed system. In this study, because of the high cost of recruiting participants from children, we set up conditions for adult Japanese native speakers to simulate phonological awareness difficulties. Applying an audio filter to the system's output simulates individual characteristics, that is, the phonological awareness difficulties. This is an experimental condition. We test the hypothesis that different audio filters produce different model preferences in the shielded task. We had two participants, both university students, and prepared two types of audio filters. This is audio sample. The original sound is this.
Godfather.
And this is a plus 10 filter.
Godfather.
Minus 10 filter.
Godfather.
Participants performed the shielded task twice, once for each filter condition, and the system has 4 models. This experiment doesn't update the models, doesn't replace the models. We are only testing the effect of the filters on model preferences. Here is the result. To see the effect of the filter, we summarize the cases in which participants selected choices that were incorrect as a schedule. In other words, when a participant makes a wrong answer. The graph shows a stacked chart of the models chosen by participants when they answered incorrectly. The vertical axis shows the number of times the model was chosen. The horizontal axis shows the participants and conditions. This is a variant of the previous graph in percentage form. It can be seen that the proportion of model selection are similar in some conditions. In particular, there is a significant correlation between participants in the +10 filtered condition. There is no significant correlation among the other conditions. This suggests that there is a consistency in model choice among participants under certain conditions, and that there are differences in model preference depending on individual characteristics and the filters that simulate them. This provides some validity to the hypothesis of this feasibility studies. Feasibility study. Summarize this presentation. We constructed a phonological awareness model using the general memory mechanisms of cognitive architecture and simulated errors in its formation process. Using the model, we designed a support system for phonological awareness formation and proposed a method for estimating an individual's phonological awareness. To verify the feasibility of the system, we conducted experiments in which individual characteristics were simulated by audio filters. There is some validity to the hypothesis that different audio filters produce different model preferences, and the results suggest that it is possible to estimate user phonological awareness through a system using personalized model. In the future, personalized models and support methods need to be more organized, and additional experiments are needed for accurate evaluation. Thank you.